Welcome to another deep dive with us. This time, we're going to tackle something
Yeah.
you literally experience every second of your life, Earth's gravity.
Right.
But we're not just talking about
Yeah.
apples falling from trees or anything like that.
No.
We're going way deeper.
Much deeper. Exactly. We all learned about 9.81 meters per second squared in school.
Right.
But,
Yeah.
there's a whole universe of nuance behind that
Right.
seemingly simple number.
Exactly.
Yeah.
So our source material today
Mm-hmm.
is from Open Educational Resources
Okay.
/ Open Source Physics at Singapore.
Gotcha.
Specifically, a section called
Okay.
7.2.7 Gravitational Field Earth JavaScript HTML5 Applet Simulation Model. Don't worry,
Yeah.
we won't get lost in all the
Yeah.
technical jargon.
Yeah.
But this deep dive is going to change how you think about gravity,
Absolutely.
satellites, and
Yeah.
even the tides.
It all starts with understanding that gravity is not a one-size-fits-all force.
Yeah.
It changes depending on where you are.
Okay, so let's unpack that a little bit.
Okay.
So the source material kind of dives into this equation
Yeah.
that might look a little bit intimidating.
Yeah.
At first,
Mm-hmm.
G equals negative GM over R squared.
Right.
But trust me,
Yeah.
it's not as scary as it seems.
No, it's actually quite elegant.
Okay.
Each part of the equation
Yeah.
tells a story.
Okay.
So G is the gravitational constant,
Right?
a universal number like the speed of light.
Okay.
M represents the mass of Earth,
Okay.
which is pretty hefty.
Yeah.
And R is the distance from
Okay.
the center of the Earth.
Okay, so that's where things get interesting.
Exactly.
This R factor
Yeah.
means that gravity isn't the same everywhere.
Exactly. Think about it this way.
Okay.
Imagine you're standing
Yeah.
on top of Mount Everest,
Okay.
feeling on top of the world,
Yeah.
literally.
Literally.
But here's the thing. You actually weigh a tiny bit less up there
What?
because you're farther from Earth's center.
Wait, seriously?
Yeah.
So
Yeah.
the farther you are
Yeah.
from the center of the Earth,
Uh,
the weaker the gravitational pull?
precisely.
Oh,
Now, the difference in weight between sea level and Mount Everest is pretty small,
right.
but it highlights a crucial point.
Okay.
The gravitational field strength
Brilliant.
is variable.
Okay.
That 9.81 meters per second squared we usually hear is just the specific value at Earth's surface.
So climbing a mountain is basically like a tiny space mission
Yeah,
where you experience slightly weaker gravity.
a little bit.
That's so cool.
Yeah.
But the source material also mentions something about G being positive or negative.
Yeah.
That seems
Yeah.
a bit strange to me.
Yeah.
Like, can gravity be anti-gravity?
Not exactly. The plus or minus sign
Oh,
simply indicates the direction of the pull.
okay.
Think of it like a magnet. Earth is like a giant magnet pulling everything towards it.
Right.
If you're above the Earth, the pull is downwards.
Okay.
That's negative G.
Gotcha.
If you were somehow below the Earth, imagine digging a hole all the way through,
Right.
the pull would be upwards.
Okay.
That's positive G.
Oh, okay.
It's all about the direction of the force.
So it's not about
Yeah.
gravity reversing.
Uh-huh.
It's just about which way it's tugging.
Yeah. Like a cosmic compass needle.
Okay, I like that.
Yeah.
Our source material also mentions a visual aid,
All right.
a magenta data line.
Yeah.
But we won't get lost in the simulation details right now.
Right.
What's important is that
Yeah.
the direction of the force plays a crucial role.
Absolutely.
Okay, and you might be wondering,
Mm-hmm.
why should I care about the specifics of G?
Right.
How does this equation actually affect my life?
Yeah.
Well, the answer might surprise you.
It might.
All right, I'm hooked.
Okay.
Tell me more.
Yeah.
Why should we care about this G business? It seems pretty abstract.
Well, for starters,
Yeah.
understanding how G changes with distance is vital for launching satellites
Oh, wow.
into orbit.
Okay.
If we didn't account for this variation,
Right.
the satellites wouldn't stay there very long.
So this seemingly abstract equation
Yeah,
is actually crucial for things like GPS
absolutely.
and satellite TV.
Exactly. And it goes even further than that.
Okay.
Understanding G helps us predict the paths of comets and asteroids,
Wow.
understand how tides work,
Okay.
and even grasp the fundamental principles
Right.
of how celestial bodies interact.
Okay, you've officially blown my mind.
Right.
It seems like this G thing is way more important
Yeah, it's a big deal.
than I ever realized.
Yeah.
And our source makes a point of distinguishing
Right.
between G,
Mm-hmm.
the general gravitational field strength,
Yeah.
and
Well-
G sub E,
Right.
The specific value at Earth's surface.
That's right.
Okay.
It's about being precise. G
Right.
is the concept.
Right.
The big picture,
Okay.
while G sub E is a specific measurement
Gotcha.
at a particular location.
Like saying fruit
So,
versus Granny Smith apple.
Granny Smith apple, exactly.
Right. Yeah, being specific is important.
It is.
So we've covered a lot about this G equation,
Yeah.
how it works, how it changes with distance,
Right.
and even the whole plus and minus direction thing.
Exactly.
What else is there to explore about gravity?
Well, now that we have a better understanding of how G works,
Yeah.
we can start to see how it affects things on a much larger scale.
Okay.
Like, how do we use this knowledge to launch satellites into orbit
Ooh, that's a great question.
and keep them there?
Yeah, I've always wondered how those things manage to stay up there
Right.
without falling back to Earth.
It's pretty wild.
Let's dive into that next.
Sounds good. So you're asking the million-dollar question.
Yeah.
How do satellites stay up there?
Right,
It
yeah.
all comes down to this fascinating balance between gravity and motion.
All right, break it down for me. It seems
Yeah.
kind of counterintuitive. Gravity
Yeah.
pulls everything down, right?
It does. But
Yeah.
here's where it gets interesting.
Okay.
Remember how we talked about G decreasing
Right.
as you move farther from Earth?
Right.
Well, satellites
Yeah.
take advantage of that.
Okay.
They orbit high above Earth,
Right.
where the gravitational pull,
Yeah.
while still present,
Yeah.
is significantly weaker.
Okay, so they're high up,
Yeah,
but that doesn't explain how they stay up.
right.
Wouldn't they just like drift off into space?
Here's the key. They're not just floating up there.
Right.
They're moving incredibly fast,
Okay.
essentially falling around the Earth.
Falling.
Yeah.
It doesn't sound very safe.
Think of it like this.
Okay.
Imagine throwing a ball horizontally.
Okay.
It travels forward,
Right.
but it also curves downwards
Yeah.
due to gravity,
Right.
eventually hitting the ground. Imagine throwing that ball
Uh-huh.
with more and more force.
Okay.
It would travel farther
Yeah, I can see that.
before hitting the ground. Right.
More force, longer distance.
Exactly.
Okay, but how does that relate to satellites?
Well, a satellite is basically that ball,
Okay.
but it's launched with so much force
Right.
that its horizontal speed
Yeah.
is perfectly balanced with Earth's curvature
Oh.
as it travels forward.
Okay.
The Earth curves away beneath it.
Oh,
It's
wow.
constantly falling.
So it's like they're perpetually falling, but they never actually hit the ground
Exactly.
because they're moving so fast.
It's a delicate dance
Okay.
between gravity
Yeah.
pulling the satellite down and its velocity carrying it forward.
So we call this free fall.
We do.
And it's the reason why astronauts on the International Space Station appear weightless,
Right.
even though they're still within Earth's gravitational field.
Exactly.
Wait, so the astronauts are falling too?
They are.
That's wild.
It is.
But it makes sense.
Yeah,
They're kind of like that ball constantly missing the Earth.
precisely.
Okay.
And this brings us back to G.
Right.
To achieve this delicate balance,
Yeah.
scientists need to calculate
Right.
the precise speed and trajectory
Okay.
for each satellite launch,
Uh-huh.
taking into account how G changes at
Yeah.
different altitudes.
Okay, this is blowing my mind.
It's pretty remarkable.
I never realized how much complex math goes into something
Yeah.
we take for granted,
Right.
like using GPS.
It's quite remarkable.
Right.
And remember, it all stems from understanding
Mm-hmm.
that G isn't a fixed value.
Right.
It's a force that changes with distance.
Right.
And by grasping that concept, we
Yeah.
can do incredible things, like
Yeah.
sending spacecraft to other planets
Well,
or positioning satellites to monitor our own.
so we've talked about satellites.
Yeah.
But our source material also mentioned tides.
Right.
How
Yeah.
does G factor into that? It's not like the ocean is falling around the Earth.
That's true.
Right.
But tides are another great example
Oh.
of G at work.
Right.
It all comes down to the
Yeah.
gravitational pull of the moon,
Okay. Yeah.
and to a lesser extent,
Mhm.
the sun.
Okay, so even though the sun is much bigger than the moon,
Mm-hmm.
it's the moon's gravity
Yes.
that has the biggest effect on our tides.
Exactly. Remember that in our equation,
Right.
distance plays a crucial role.
Okay.
Even though the sun's gravitational pull
Yeah.
is much stronger overall,
Uh-huh.
the moon is much closer to Earth.
Right.
And that proximity means
Yeah.
its gravitational influence
Right.
on our oceans is stronger.
It's like that saying, location, location, location.
Exactly.
So the moon's gravity tugs on the water
Yeah.
creating bulges that we
Yeah.
experience as high tides.
Yes.
That's so cool.
It is. And the Earth rotates beneath these bulges,
Right.
which is why we experience high and low tides roughly every 12 hours.
Oh, okay.
It's a constant push and pull.
So this is making me see gravity in a whole new light.
Yeah.
It's not just about things falling down.
Yeah.
It's about this
Right.
intricate dance of forces
Yeah.
shaping our world
Mm-hmm.
and even the cosmos.
You got it.
Okay.
And we've only scratched the surface.
Right.
There's so much more to discover about this
Yeah.
fundamental force
Yeah.
of the universe.
Well, we've covered a lot of ground today,
We have.
from the equation for G to satellites and tides.
Absolutely.
It's amazing how much there is to unpack
Yeah.
about something we experience constantly,
Right.
but rarely think about.
It's amazing.
Yeah.
Exactly. It's all about
Right.
asking those questions.
Yeah.
And diving deeper.
Speaking of questions,
Yeah.
before we wrap up this gravitational adventure,
Mm-hmm.
I think it's time for one final thought-provoking question
Okay.
to leave our listeners pondering.
Let's give them something to chew on.
Okay, so listeners, we've talked about how gravity changes with distance, right?
Right.
And how satellites are essentially falling around the Earth.
Yeah.
But this begs the question,
Mm-hmm.
if gravity gets weaker the farther you are from Earth,
Right.
how do satellites stay
Yep.
in orbit
Okay.
without just flying away?
Yeah, that's a great question.
Yeah.
It's all about finding that sweet spot
Okay.
between the satellite's speed
Right.
and the pull of Earth's gravity.
So it's like a cosmic tug of war.
Yeah.
Gravity's pulling down,
Yeah,
but the satellite speed is trying to fling it outwards.
exactly. If the satellite were moving too slowly,
Yeah.
gravity would win, and
Ex-
it would spiral back down towards Earth.
A fiery demise for our satellite.
It would not be good.
But what if it's going too fast?
Then it could escape Earth's gravitational pull altogether
Oh,
and zoom off into space.
Oh, no.
Get lost forever.
Okay, so it's all about finding that perfect balance.
Yeah,
Not too fast, not too slow.
Yeah.
It's kind of like Goldilocks.
like Goldilocks.
But with orbital mechanics.
Exactly. It's about finding that precise speed
Right,
where the satellite is constantly falling towards Earth,
right.
but its forward motion keeps it curving
Yeah.
around the planet.
Okay.
Essentially forever falling,
Yeah.
but never hitting the ground.
This is blowing my mind.
It is pretty amazing.
It's like a perfectly choreographed dance between gravity and motion.
It is, and it's all thanks to
Yeah.
our understanding of G,
Right.
that gravitational field strength we talked about earlier.
Right.
Scientists use that knowledge to calculate the exact speed and trajectory needed to launch a satellite into a stable orbit.
Wow. So much science and calculation goes into something
Yeah, it's a lot of work.
that we use every day without even thinking about it.
Absolutely.
It's amazing.
It really is. And it highlights
Yeah.
how important it is to dive deeper,
Right.
to understand the forces
Mhm.
that shape our world
Yeah.
and the universe.
Right.
Even something as familiar as gravity
Yeah.
has these hidden layers of complexity and wonder.
I think we've given our listeners a lot to chew on today.
I think so.
We've explored the equation behind gravity,
Mm-hmm.
learned how satellites defy the pull of Earth,
Yeah,
and even uncovered the secrets of the tides.
that's right.
And we've seen how understanding a seemingly simple concept like G
Right.
can unlock a deeper understanding of the universe around us.
Absolutely.
Exactly.
Yeah.
So to our listeners,
Yep.
keep asking questions,
Keep diving deeper.
keep exploring, and never stop diving deeper into the world around you.
It's a fascinating place out there.
Until next time, keep looking up.